Well, it's absolutely a great honor, really, to receive today the medal of sorry. The eyes medal, and I'm sorry, my emotions cannot stop. It's really a pleasure, really, and to receive this prestigious award, you know, which is so important for me. We have started, you know, 11 years. We came with Marcel, my wife, in 1978, and we stayed 11 years at the University of Michigan. I'm sorry, the Rochester, and we made so many contributions because this place is absolutely fantastic. It was, of course, you know, the cradle of optics here in the United States, and also he had these fantastic schools, which is in Institute of Optics, where so many brilliant students, you know, were really trained and taught. And I had the chance, really, to work with them. I had the chance, really, to be helped by them. And they are, for me, like a, like a family, my kids. I just want to mention students like Donna Strickland, of course, with whom I did the CPA. I'm going to talk about the CPA in a few minutes with what CPA made possible. Also, Yanis Valmanis with the electro-optic sampling, Steve Williamson, who is in the attendance here with the electron diffractions, Dan Blumenthal with the terahertz, and John Nees and Todd Sizers and Earl Dooling and so on. I think with a little bit with Yin, who's here. Yin also did a little bit of work in my laboratory, you know. So all that, you know, I'm absolutely, you know, very emotional for me to be here, you know, because on top of that, of course, it's the 100th anniversary of the OSA. So I really would like to thank the OSA. I would like to thank people who nominated me for this prestigious award, and people in the selection committee who selected me to get it, okay? So I really thank you so much, Rochester and the OSA, you know, to have given me the possibility really to accomplish so much. So I'm going to, now I'm going to start my talk, and it is based, as I said, on the work that we did with Donna Strickland. Hello, Donna. And it's about a way, in fact, to connect now, optics with high field physics. And that's the reason why we have these two personages, these two icons. One, of course, you will recognize immediately, is Charles Towns, and the other one, maybe not, but is, of course, Higgs, you know, Peter Higgs, the scientist who predicted, you know, the new particles, the Higgs new particles. And what I want to say in this is what's exciting right now about optics, and that it's maybe with optics that we will be able really to go to beyond the frontier in terms of high energy physics. And and this is what I would like really to talk about. If I had a chance to have a, oh, here it is, okay. So here we go. fine. So basically, optics is in the electron volt scale, okay? And so what I wanted to show is that there is plenty also of room above the electron volt, okay? And right now, what we are going to describe is the fact that we are in the EV scale, and optics, most of you are in the EV scales, but now there is ways to go and to think and to go into GeV and TeV scales. And this is very exciting, which means that optics right now is in the atomic world, okay? And with going with GeV and TeV, we will be really in a subatomic. So there's these transitions I would like really to discuss. So how can we do that, okay? So of course, it's a very ambitious program, but so how we can do that? Well, in order to do that, to go from the EV optics to the GeV and TeV optics, we are going to need power, okay? Very, very high peak powers. Powers, which is in a petawatt regime, which is about 1,000 times the power, the grid powers, okay? And of course, we are developing this power only for 15 femtoseconds, okay? So the other thing is we need, and we'll need, is of course we will need the very high intensity, which is going to be obtained by focusing this power over a very short spot size of the order of the wavelength of light, of course. And that, of course, this is going to lead to extremely high pressure. The high pressures of, I don't know, many millions of Eiffel towers on the tip of your fingers. That's the type of things that we can do. And this is the roadmap of intensities, because it is by getting the intensity very high, as I said, that we will be able really to go into this, to segue between the EV to the TeV. And when we started the lasers, laser was the power or the intensity was in a range of 10 to the 8 watt per square centimeters, Then, but that was enough, for Peter Franken and Nico Bloembergen really to develop, what we all know now is really the nonlinear optics. Then we went up to 10 to the 14, 10 to the 15, and it was a realm of laser fusions, and multiphoton ionizations. Okay, I'm really pleased also to see that Joe Eberle is here, which has really been very important for this field. And then, well, I mean, at that time, the intensity plateaued to 10 to the 15, 10 to the 16. And in order to go higher, I mean, we had to develop something. And this, the trick was done with Donna and myself, where we say, well, in order to increase the peak power, what we will do is we can stretch the pulse, amplify it, compress it, and immediately we were able really to produce extremely high peak powers. And then we'll be able really to go into new regimes, okay? The first new regime was what we call relativistic optics, okay? Well, of course, photons are relativistic, but in this type of optics, it's the electrons, oscillating in the field of the laser, which is reaching, the speed of light, okay? And so this is, that changed the game completely, okay? In fact, it will give us the possibility to accelerate particles to extremely high energy, okay? I will show you. So at around 10 to the 18, the electrons becomes relativistic, and then at the 10 to the 26, 10 to the 24, 10 to the 24, 25, then it's really the proton now, which is much more massive, will become relativistic, okay? So, and so this is a new regime. And this is at 10 to the 24 or 10 to the 25 watts. This is a goal for the infrastructures, Eli infrastructures, to get to develop this regime. Now, the Eli infrastructure is a combination of three very large-scale infrastructures. One, and I guess maybe I can show. Yes, one is in three really very, very impressive facilities. One is at Prague. The other one is in Hungary, in Szeged, and the final one, which is in Romania, in Bucharest. Okay, and Europe, decided to build these three facilities in order to study what this regime at 10 to the 24, 10 to the 25, the regime where the protons are relativistic. And also the regime where, if we are a little bit lucky, where we could really break down the vacuum. We could really make pairs, and we could, from the light, we could really turn light into matter by making pairs, electron-positron pairs. Okay. Now, this is where I would like to spend some time. Is what is exciting also is above this 10 to the 24th. You are marching toward 10 to the 29, 10 to the 29. Watt per square centimeters, where precisely you are really, this time you are really creating a massive amount, a soup of electrons and positrons. And this is really a regime where we would like to go, okay? In order to do that, of course, it is a problem because if we already, in order at 10 to the 24, we have to increase the power by 5 or 6 orders of magnitude. And in order to do that, of course, we cannot increase the size of this very, very large building already, this very large laser by factor 10 to the 5, 10 to the 6. So we decided to investigate a shortcut. And the shortcut will be that instead of trying to increase the energy, keeping the pulse duration constant or about, then we would like right now to decrease the pulse duration. Okay? So if we could, for instance, we are in a femtosecond regime right now, and if we could really go into the attosecond regime, then with only 1 joule, for instance, in 1 attosecond, it's an exawatt, okay? And we should be really able to get very easily into this Schwinger domain I just talked about. Okay, so so how do we do that? So we decided to go for shorter pulses, and the first thing to do was to compress the pulse. The pulse, which is already at 20 femtoseconds or so, we would like to compress it to the single cycle regime. Well, we knew that single cycle was already shown at Bell Lab and so on. I mean, few optical cycle. We have this very, very famous experiment where people in a Chuck Shank group and Wayne Knox and Yanis and Jim Kafka, if he's here, were involved with this experiment where you use the fibers, in a fiber where you are producing self-phase modulations to gain bandwidth and group velocity dispersion. Then they were able really to demonstrate the 6 femtosecond was 3 optical cycles, or 2 optical cycles. Then this is, you are at nanojoule level. If you do that now by using capillaries, then we could, Horacio Svelto showed that we could get, and also Ferencvaros, we could get into this millijoule level. Okay. Well, so we are now in the millijoule level, and we can really compress the pulse to few optical cycles. Okay. But what we would like to do, in fact, is to compress now tens, hundreds, thousand joules to the single cycle, okay, in order to jack up the pulse, the power. And what we do is now, this is work in progress, okay? We would like to use the fact that lasers putting out very large energy have flat top. And if they have flat top, then I can really put a thin piece of plastic or something like this, and I can produce self-phase modulations and group velocity dispersion, completely, uniformly across the beam, okay? And we should be able to produce really single cycle pulses of hundreds of joules, okay? This is mind-boggling, of course, you know. So this is by using thin film of plastic. We do that, so it's very easy. And so we use this petawatt system, but you know, now you can buy by a few companies making them. And they have this flat top beam. And now if I'm doing the following experiment, I take this flat top beam, and they're in a 25 femtosecond regime, and they go through this plastic, and then they get self-phase modulation, group velocity dispersion, they spread, and with a chirp and so on, and then we recompress. We recompress now with chirp mirrors, and we can really compress. After 2 stages, we can go to few femtoseconds, okay, single cycle, okay? And so this is, of course, mind-boggling. And it works really nicely right now. We started on a smaller scale, but it seems to work nicely. Okay, so once you have a single cycle, you like to go much, much shorter. You like to go into, as I say, attosecond and maybe zeptosecond regime. And so how can we do that? Trying to compress the pulse, which is already single cycle invisible, into going to attosecond and maybe zeptosecond regime. Well, we are using this trick, which is, trick is a little bit better than a trick, is the technique of relativistic compression, okay? Now, if you have this single cycle, which is coming on your left, coming on your target. The target can be metal, can be plastic, whatever. And what's going to happen is the intensity is absolutely phenomenal, okay, as I showed, So the intensity is going to push the electrons, okay, first. The ions are going to stay in the back because they're too heavy to move. And what we are going to do, we are, going to form this concave mirrors, which is going to move now because you have this very fierce force. You have separated the electrons and the ions, and now they are going to move toward, the lasers at the speed of light. So you will have the laser going at the speed of light, the mirrors going at the speed of light, and But you know that the reflections is also going at the speed of light. So he has no choice but to have that leads to compressions, okay, of the pores. And the compression can be very high. It can be 1,000 times, okay? So we can go to 2,000, even more, because, I mean, we have simulations. So here I show the phase where the critical surface is moving out. So we have simulation which shows that we could get zeptosecond, okay? So of course I don't think we'll get the zeptosecond, but I mean we could get very, very short, okay? Of course this is fabulous because if you have attosecond, zeptosecond, there will be X-ray or gamma rays immediately, okay? And this is extremely exciting because we have low-hanging fruits, you know, like, for instance, we'll be able, I will show you that we could produce very, very high gradients to accelerate particles over very, very short distance. You know, right now, typically, we can accelerate particle of, say, MeV per centimeters, okay? MeV per centimeters. But if you want to do to 10 to the TeV, will take you 10 to the 6th centimeters, it's 10 kilometers. So Toshita Jimas, in 79, you know, had the idea to use, and this is pretty standard, what we do, to focus a beam into a gas, and producing a plasma wave. This plasma wave is going to move the particles, you know, at the speed of light, okay? But these times, with gradients of 10 to the 9, okay? 10 to the 9 GeV per centimeter, 10 to the 9 EV per centimeter, okay? Now, I mean, everybody have seen, you know, synchrotrons and so on. They are GeV machines, okay, and they take kilometers in circumference. But here you see that we could really produce, I mean, I think that has been done already. We can produce GeV over centimeters, okay? But if we had X-rays, and by compressing our pulse and so on, what would happen is we can use not gas, you know, which is low density. We can use solid now, okay? Because the X-rays can go through solids, okay? And then we could get in a regime of 10 to the 12, that is a TeV per centimeters, which is, of course, is very mind-boggling. I just put here these slides on scale where we shows from the 27 kilometers TeV machines from CERN, okay? And on the red, if you see it, I put the 100-meter machine that we could really produce with gas technology, okay? And if we are using solid technology with the X-rays, then it will be really, okay, yes, I think so, okay. It will basically, the TeV that is CERN will be on a finger, okay? So this is really, of course, phenomenal. And of course, we can have, this is going to be a game changer. We have many applications, scientific applications in laser astrophysics and cosmology, polarizations of vacuums, materialization of light beyond the standard model. You know, we could really, the X factory, we could study dark matter, certainly. It will be absolutely a completely revolutionary tool. Now, of course, it's important to have applications. And in the applications, you know, we have, for instance, because if we are able really to produce this, accelerate this particle over short distances, we can increase the size of instruments like and some which are used in medical world, where we, for instance, where we can accelerate protons to do proton therapies, which is really the best way now. I mean, what we say is the best way maybe to cure cancer. So we could really proton therapies with the proton produced by the lasers. We could also produce isotopes, for imaging, but also for treating, patients. And also with this very high flux of particles, protons, we can produce neutrons, and then we could really one day maybe, and that will be of course fantastic, will be really to treat nuclear waste, and so this is, of course, this is what is coming. This is what really the laser can still offer, and I hope that the next century, I guess very few people will be here to see it, but we will be able really to see many more applications of lasers. And for me, it's very clear that the laser is over 50, 56, but we have not seen everything yet. I think the best is yet to come. Thank you very much. And happy 100th anniversary to OSF.